All right. So and the final thing that final problem that also I think so everyone got is a sphere and a torus. Okay, and this also, so this are not homeomorphic because the Euler characteristic or the Euler number, let me just call it numbers, the Euler numbers are different. Okay, and Euler number is a topological invariant. Okay, so so this for the sphere, the Euler number we saw was 2, and for a torus it was 0. Right, so so this distinguished between the sphere and a torus. Okay, so so let me say that the basic problem of topology. Okay, so the so the basic problem, the fundamental problem that this field tries to solve is given two topological spaces. Now you can imagine metric spaces. Let's say call them X and Y. Are they homeomorphic? Okay, are they the same in terms as topological spaces? Okay, so you might have sort of different descriptions of them, etc. So can you find a continuous bijection as inverse is continuous? I mean, are they the same topological space? And so so things like Euler numbers are interesting because so they are topological invariants. Okay, so I mean the one sort of strategy the topology this field has developed is to come up with various topological invariants. So you need these topological invariants like Euler number, etc. Which doesn't change under homeomorphisms. It's invariant under homeomorphisms, right? So if two spaces, if you have an invariant like Euler characteristic, and they are different, then you would know that the two things are not homeomorphic. Okay, so they are very good at saying whether two things are not homeomorphic. Okay? So these topological invariants are needed. So before I mention some other, some more examples of topological invariants, let me just say, a little bit about why do we care, right? So I mean, it's okay. Also, I mean, you have this notion of topological spaces, some open sets, etc. Why do we care whether things are homeomorphic or not, and things like that? So it turns out that these shapes, so these let me just use some other color perhaps. That these various shapes, these topological spaces, these topological, let me call this topological spaces, arise often in the sciences, okay, and be it in engineering also, okay. So I mentioned that it's used in robot, motion planning, etc. I'm sure even architecture would have some space. I mean, so these topological spaces, geometric shapes, of course, arise. But so let me now mention a few things about how it arises in science. It might arise in data plots. Okay, this is a very big thing now. I mean, so all this big data and all the people, Google and all are collecting so much of information. There's so much of sort of numbers and charts and plots. And how do you make sense of them? So one way is to use topology, and that is being used. So one of the applications currently. So the data plots, and then sort of maybe it's image processing. Let's say you're comparing shapes of a healthy brain and somebody with some sort of disease, and then you're trying to sort of compare these images and phase diagrams. This is sort of goes back to the 19th century where sort of initially all this subject started. You're trying to see the motion of some sort of object, and then you construct a phase space, right? And these are all topological spaces, and so it turns out that these when you have these shapes arising, so often what is needed, often what is really important is not something about the the distances between things, how what the geometry of the shape is, but just the topology. Okay, so what is important is the topology, okay, and not the geometry. Okay, so let me tell you, I mean, historically, the way sort of these ideas first arose was, I mean, a lot of these notions in topology, the first notions were due to Henri Poincaré, who was this mathematician, French mathematician in the 19th century, and he, in his 20s, he kind of came up with this because there was a problem. There was a prize problem. This academy in some academy in France had posed, and about whether the solar system is stable or not. So this was a time when maybe some people were concerned about this. So the planets are revolving around the sun. Now by that time people knew there was gravity and there was Newton's laws, etc. They didn't know Einstein's sort of theory of gravity, but they knew about Newton's laws, etc. And the problem was whether this solar system will remain like this, or whether things will collapse into the sun, or what's the deal. And so it was during the process of sort of attacking this prize problem with that Poincaré developed some of the notion. I mean, so here, I mean, what is essential is not perhaps more the geometry of, I mean, you don't care perhaps how long it will remain stable, but the question is whether it is stable or not. So there's there are places where the notion of topological equivalence, you're caring about topological equivalence rather than any other more rigid notion of equivalence makes more sense. Okay, and so this is why topology and the basic problem in topology, sort of understanding when topological spaces are homeomorphic, is important, and it's used. And some of these notions, these invariants that have come up today, are used in physics and used in engineering, and they are and sort of potentially there's going to be always more and more uses will always be discovered. Right? So in any case, this is what the basic problem in topology is. And so far, I mean, so we've seen the topological invariants, and some of them are as follows. So we have seen Euler number. This is only for surfaces. Okay, so for surfaces, where if your topological space is a surface. So let me define what a surface is. This is something that I promised to do also. But let me sort of do it after I list a few other topological invariants. So then you have orientability. This is again for surfaces. And then, so what other invariants are there? So there is a notion of, if you've been reading this Armstrong's book, you know that there's a notion of compactness. So that's a topological invariant. There's the notion of connectedness. Okay, so these are all topological. And anyone suggest anything else? So there's only one. Well, in any case, these are the sort of perhaps the most basic ones. And as you go further in topology, you'll find more and more invariants. Yeah, anyone? Yeah. I forgot. Somebody was asking in the group about the other problem, right? This about. I just completely forgot while discussing about the problems that there was this puzzle that I had asked you guys to solve. Okay, so that is okay. So somebody asked this. So it is not a topological invariant. What is not a topological invariant? Well, being the property of being covered by disjoint. Pairwise disjoint. By disjoint, I mean pairwise disjoint. Okay, line segments, straight line segments. Why is this not a topological invariant? Because so maybe in one space you can cover. Let's say this guy you can cover by line segments. But if you have a homeomorphism, F, the other space I was looking at is triangle, right? Well, here the homeomorphism need not take straight lines to straight lines, right? It's just some continuous map. So, this might be some wavy thing. So it doesn't really answer the puzzle. Okay, so this notion of homeomorphism doesn't quite immediately answer the puzzle. So the puzzle is something where you have to think a little bit differently. Of course, this might give you a clue, but it's not the same. So let me sort of do that puzzle question, which I forgot about. So it's the sort of the opinion seems to be divided, and some of you think you can't do it, some of you think you can, some of you don't. So let's let me tell you what the answer is. So the answer is you can. Okay, so your triangle, of course, the obvious one doesn't work, right? If you take the triangle and take sort of lines parallel to one of the sides, then these sort of ultimately become a point, right? So that's not allowed, right? It's not a you want a line segments, as I said, of some positive length, right? So that's not allowed. But what you could do, so you could get inspired. I mean, so you could get inspired on the fact that a square is homeomorphic to a triangle in the following way. You can try to sort of imagine a homeomorphism that does take straight lines to straight lines. Okay, so one way of thinking about it is, so maybe you take that corner vertex here. Let me use another color, corner vertex here, and you kind of push it in. Okay, so imagine it's some kind of sort of made up of some kind of flexible rods, and you have this corner here, and you sort of push it in. And so when you push it in a little bit, what happens? What do you get? Well, so when you push it in, you can make sure that these straight lines remain straight. Okay, so this so you kind of so this the slope of the lines as you go to the right might be sort of getting tilted, sort of deviating from the vertical, but as you go, sort of this it's still, I mean, it's foliated. This trapezoid is still foliated with lines, and if you can keep pushing it until it's sort of all in one line. This vertex, these three vertices that were originally in the top left, top right, and bottom right, these three, you can push it so you sort of let me say, you sort of push in and until they're straight, and then so this resulting thing will still have some kind of foliation with straight lines, and there will be one of the lines will be, yeah, so this guy here. Okay, so can people imagine, right? So it's maybe I'm not drawing it, and you can make this precise. You can actually write down the equation. I mean, so essentially you have sort of these two line segments. Let me just so this part here, maybe I should use another color, so brighter color, perhaps orange, right? So you have this line segment and you have this line segment, right? And you're kind of looking at all the lines, sort of between. So you're parametrizing, let's say, this bottom line as you go, and you're parametrizing the top line, and as you go along them, you're looking at the line in between those 2 points. Okay, and so you can make, just like this is what happened even on a square. So on the square you had sort of this edge and that edge. Okay, and you're looking at sort of as you go along them, you look at lines joining these points. You do the same thing now with this sort of this part of the triangle. This is not a complete edge of the triangle, but only a portion of it, and then another edge of the triangle. And so you can see that you can foliate. This is called a foliation, by the way, but you can sort of cover the triangle with these lines. Okay. All right. So yeah. So coming back to topological invariants, so you have various things, and let me just say that sort of later, and when you do algebraic topology, it turns out that there are other topological, so another important topological invariant is a group. Okay, so it's something that you learn in algebra, right? So this topological invariant is called the fundamental group of a topological space. Okay, so so this turns out to be a a group, and so this is in a very important topological invariant. So once again, I mean, homeomorphic spaces will have the same fundamental group. That's the whole idea. Okay, so so these topological invariants are very useful, and let me tell you how. Well, we've already seen how for a surface this completely solves the basic problem, at least for closed surfaces. Okay, so so let me just now so let me just mention what I said. So the basic problem in of topology, and so the basic problem. Let me just not. So basic problem is solved for a closed surface, right? This is basically the classification of surfaces. And so let me define more carefully what a surface is. So it's something I promised to do much earlier. So a surface is a particular kind of topological space. I'll think of it as a metric space, which is sort of easier to imagine. So it's a metric space such that it looks like, you know, the plane, right? At every point, it looks like the plane. So how do you view it mathematically? How do you write it mathematically? So each point in S has a neighborhood. So this neighborhood you can think of as a metric ball, right? A metric disk, as a neighborhood that is homeomorphic to R2. Okay, and I also require. So let me write R2 somewhere else so that this is called, it's locally looks like the plane. Okay. And the second thing that I think Armstrong doesn't mention, but it's you know, in all other definitions of surfaces that you would find useful much later, there's a very technical requirement that S can be covered by countably many such neighborhoods. Okay, this is called second countability of the space.